Alright, the next topic is on precision. Like accuracy, precision is related to exactness, but it's determined by the limitations of the measuring instrument. Maybe a good way of saying this is how finely is the measuring instrument marked. Okay, so the precision is, for example, if you think of a ruler like that we just looked at a minute ago or in the last lesson, the finer the little marks are, the more precise it will be. Okay, maybe that's the best way to look at this. Let's go look at that last example we had here, or not last example. This top ruler is more precise than the bottom ruler. Okay, doesn't have anything to do with accuracy. It's more precise. In other words, it has finer markings. Okay, so let's put that in here. The precision is determined by the limitations of the device. Okay, the smallest unit of measurement on the device. Okay, so the more precise, the finer the units of measurement. Okay, determining degree of precision. So Greg is redecorating a bedroom in his house. He knows that his measurements need to be accurate, but the degree of precision requires depends on the job. Greg wants to determine how much paint to buy. The dimensions of the room are 12 feet, 81.5 inches by 10 feet, 10 inches. The ceiling is 10 feet and a half high. What degree of precision does he need for the room's measurement? How much paint should he buy? Okay, you don't have to be very precise here. Don't need to be precise. Why not? Well, if you think about the way paint is bought, you're buying gallons of paint. The chance of you buying the exact amount of paint that you need are almost impossible. You're probably going to need to buy more than you need. And that might be for touch-ups later. It might be because you made a mistake or anything like that. Okay? So you don't need to be very precise in this case. Okay, what degree of precision does he need for the room's measurements? Well, I guess we could stick to inches because that's what it's at. Okay, so let's figure this out. So first wall would be here. Okay, let's figure out how big each of these rooms are. So 10 feet 10 inches is this wall right here. 12 feet 8.5 inches is this wall here, and the ceiling is 10 feet and a half inches high. Okay. Wait, that's not what it says here. Should be the ceiling is 7 feet 10.5 inches high. So if I want to do this wall right here, what I'm going to do is I'll go 12 feet 8.5 inches. Okay, and I'm going to multiply that by 7 feet 10.5 inches. Now, do I need to be that precise? Do I need to know exactly by how many inches it is? I don't think so. So instead of doing this, I'm going to say this is about 13 feet. And I'm going to say this is about 8 feet. Okay, so if I multiply that, I get 13 times 8, that's 104 feet square. Okay, then I'm going to try the other wall. It's 10 feet 10 inches, and it's also 7 feet 10 inches, 10.5 inches high. Again, I'm going to round that off to 11 feet and 8 feet. So this is 88 feet squared. Okay, so what is my total? Notice I'm not even accounting for the fact that there is a door here, because I'm probably not going to paint that. What I'm going to do is I'm going to say one wall is 104 square feet, another one is 88 square feet, and you can see that each of these walls, there's two of them. Okay, so if I put that all together, I end up with 384 feet squared. Now it did say that I'm going to paint, did it say that I had to paint it twice? Usually with paint you're going to have to use two coats. Very little paint works after just one coat. So I'm going to go 2 times 384 feet. And so I get 768 feet squared. That's how much I would need to cover. And you could even think of this as about 750 feet squared, just to kind of round it off. Okay? So that tells you about how much area there is. Then you would say, with a can, how much does a can cost? And you'd have to figure out how many cans you would need. Okay? Greg is also replacing the door and window casing. The door frame measures 80 inches by 30 inches. The door casing will be installed so that about 1/8 of the door frame is exposed. Greg needs to cut the pieces of casing. What degree of precision does he need for the measurements? Okay, this needs to be precise. You can't even be off a little bit. Okay, so if we think about this joint right here, what you're going to have is a piece of wood that joins at an angle like this. Okay, if you don't make this cut perfectly, there's going to be a space there. You don't want a space there. So this needs to be exact. All right. So let's read it carefully. The door casing will be installed so that about 1/8 inch of the door frame is exposed. So that means we're just going to go a little bit bigger in each case. So 80 inches plus 1/8 of an inch equals 80 and 1/8 of an inch. All that means is, if here's the door, this piece that we're putting along here is going to go a little bit higher. It's going to go a little bit past the door so that we have a little bit is exposed on all the way around the door like this. Okay, that's why we're adding 1/8. We're going a little bit above the door. Okay, and then the top part will be 30 inches plus 1/8 because we're doing it on each side. So this is 30 and 2/8 inches. Okay, which you'll probably see as 30 1/4 inch. Okay, so that's what you're going to have to cut the pieces at, those lengths. All right. Another part of precision is the idea of significant digits. Okay, the number of significant digits in a measurement shows how precise the measurement is. You need to know about significant digits when you multiply or divide measurements. Okay, so looking at this chart, non-zero digits in all numbers, all non-zero digits are significant. If they're there, they're important. Okay, zeros and decimals, they're only significant if they appear to the right of the first non-zero digit. Okay, zeros in whole numbers are significant only if they appear between non-zero digits, and zeros at the end of a whole number are ambiguous. Okay, so what does this mean? Okay, well, non-zero digits, yes, these are all important. Okay, zeros and decimals, what are the significant figures? Okay, each of these have 4 significant digits. Here are the 4 here, and here are the 4 there. Okay, zeros in whole numbers, these are both 3 significant digits, and this one, it's impossible to tell if those 2 zeros are significant or not. We would have to have some more information. Okay, so let's do some examples so you understand this. Okay, which measurement matches each number of significant digits? Okay, which one has 1 significant digit? Only 1. All right, I think that would be this one. Okay, just the 4 is significant there. Which one has 2? Okay, this one you can see there are 3, so it's not that one. This one has more than that. It looks to me like this one is going to have 2 significant digits, the 2 and the 5. All right, which one has 3? Okay, this one has 3. Why doesn't this one have 3? This one actually is 4 significant digits. Well, the reason this 0 has been put there, it must mean that we know there is 0 there. Okay? For example, if the number was like this instead, we don't know if this was really a 0 or if it's been rounded off. On the other hand, if that 0 is intentionally put as a decimal, we know that it's a significant digit. Okay, and then this one is 5. All right. When you add or subtract, round the final answer to the same position as that is in the least precise measurement. In other words, the fewest decimal places. All right, let's try this one. So if we're going to add these up, 5.241 plus 3.845 plus 0.76. Okay, which one of those is the least precise? All right, you should be able to see that this is the least precise because it only goes to 2 decimals. So when I answer this, I want to go to that decimal. Okay, so I'm going to add this all up. I get 17.412, but because the least precise decimal is the 100ths, I am going to round this to the 100ths. I'm going to stop there. This 2 I don't know about. Okay, it's not significant. So how should they report the length of the baseboard? The least precise measurement has 2 decimal places. This means that the length of the baseboard should be reported to the nearest 100th of a meter. Okay, Jen and Max should round up because, all right, so the question here is, should I buy 17 meters or 18 meters? You should round up because they will not have enough baseboard if they round down. Okay, so they will need 17.42 meters of baseboard. That would be the exact. Chances are if you were ever going into the store, you'd probably end up buying like 18 meters. Okay, but we're trying to be as accurate as possible here, precise as possible. Okay, so let's do the same question here. Which one is the least precise? Right here. So that means we're going to round to the 10th right there. So let's add those 3 up. If I add them up, I get 10.296 feet, but I have to round to the 10th, so this is going to be 10.3 feet. Okay. A jug has 2.5 liters of juice in it. You pour out 1.268 liters. I have no idea how you would know you would pour that much out, but that's what we're being told. So if I pour that out, I end up with 1.232 liters left. Okay, but what's the most significant, or this is the least precise? So our significant figures is the 5, or that's the 10th. So I'm going to round this, and I'm going to say there is 1.2 liters left. Okay. When you multiply or divide, round the final answer to the least number of significant digits in the measurements used. Treat whole numbers as having an unlimited number of significant digits. Okay, so here you have 3 sig figs, significant figures. Here you have 4 significant figures. Okay, so if I go area is length times width, which is going to be 12 times 10.25, I end up with 123, and that is 3 significant figures. All right, so what did it say? It says when you multiply or divide, round the final answer to the least number of significant figures. Well, we wanted 3. This is 3. So this is good, because that's the least. Okay, let's try another one. This one has 3 significant figures. This one, 6 millimeters. Okay, now what did it say here? Treat whole numbers as having an unlimited number of significant figures. So unlimited. So if I go volume is pi times radius squared times 34.1. The volume turns out to be 3,856.619 millimeters cubed. Okay, and I need to go to 3 significant figures. So what I'm going to do here is I'm going to go to, this is the third one, this will round up, and I will have 3,860 millimeters cubed. This has 3 significant figures. All right. So, assignment 2. Give it a shot, and we'll discuss it in class tomorrow.